Hello everyone, welcome back to this channel. So we are in the series of lecture on probability and statistics in data science. Okay, in that series, in the last video we have discussed about probability distributions, binomial distribution, Poisson distribution, which comes under discrete probability distributions. Under continuous distributions, we discussed about normal distributions. So those who have not watched that earlier video, I would recommend you to watch that video. If at all, if you have planned to watch this video on sampling distribution and standard error. This video, we are going to discuss what is sampling distribution. And what is the intuitive understanding of standard error? That also we are going to discuss. Standard error. Standard error of what? We are going to discuss this. So the broader perspective of this discussion is inferential statistics. So the scope of inferential statistics we are going to infer a population parameter. Okay, if the parameter which is quantitative variable, we are trying to infer what is the population mean value. If it is a qualitative variable, we'll be inferring the population proportion. I'll give you example in both the case. We are going to see the example in both cases. So we should understand certain terminologies attached to samples and populations. The sample mean generally we used to represent as X bar. Some standard textbooks uses either Y bar also. Whether I use X bar or Y bar doesn't matter. X bar or Y bar. The standard deviation of the sample is usually represented as lowercase s. And of course, the variance is represented as S square. And the number of samples, lowercase en. Pertaining to the population, we use these terminologies. The population parameter, mean of the population is represented as mu. Standard deviation is represented as sigma. Variance is represented sigma square. And capital N represents the total population, size of the total population. The primary objective here is we need to estimate the population parameter. The moment I use the word estimation, as I already mentioned in the earlier videos, point estimation of this mu is impossible practically, right? This point estimation practically is not possible. Only the range estimation is possible, range. So the sampling distribution is going to give us the notion of how do we are going to estimate this population parameter, either population mean or population proportion, with a range. So this range, we are going to introduce the term called confidence interval range. I mentioned you better to watch the normal distribution discussion as what we discussed in the previous video. Better to comprehend this confidence interval range. In the last video we have discussed the empirical rule for standard normal distribution. Okay, the distribution of the samples from -1 sigma to +1 sigma, -1 sigma to +1 sigma, 68% of the samples are distributed in this range. Between -2 sigma to plus 2 sigma, we have around 95.5%. So if you round off this to 95%, so for 95%, precisely at 95%, what is the range? What is the range of this sigma ranges? We can say this point is 1.96 sigma, and this portion is minus 1.96 sigma. So in the bandwidth of minus 1.96 sigma to plus 1.9 sigma, we can have 95% of the distribution of the sample if you are approximating the sample to close to near normal distribution. So keeping this point in idea, we are going to explore this. So how do we do the range estimate of population parameter mu? Okay, that is the focus of discussion today. So having said that, what is the logic here is, because the population distribution or the entire population, nobody can have the access in the reality. That is why we go for the inferential statistics. Because your population is ever growing population. Suppose, let us say, I wanted to estimate the average age of the newborn babies in India. What is the average age of the newborn babies born in India? A full term, okay, for a full term. If at all, if you try to access the exhaustive population, by the time you go and collect the population, there are few other new babies will born. At the same time, we know the mortality rate of the newborn babies also. So by the time you go and access the entire data set of the population, your population data set is ever fluctuating, ever varying. Practically accessing the entire population, the exhaustive population data is not feasible. So that is the reason we go for inferential statistics. So now I have a two scope. I'm going to discuss the two solution to this. One is a very theoretical solution, but it is less feasible. Number two is more practical. Okay. So let us talk about a very close approximation. I would say very close approximation, but it is a bit expensive process. I would say it is an very expensive process. But it is a very close approximation. Approximation in the sense, whatever the estimation you do, we can do it with the minimal error. The another method, which is a more practical approach, very practical approach. Of course, it is a less expensive. I will tell you on what context I'm saying it is an expensive or less expensive is. Once you understand the whole process, we can appreciate this. The logic here in the most theoretical approach is, this is the population. Okay, shortly I'm going to, after this discussion, I'm going to simulate this in Python. I'm going to show you. Okay, let us simulate some 50,000 sample as a population data. Let us assume. Okay, this is a population data. I'm going to simulate some 50,000 samples as a population data. Since we only simulating the data, so the population parameter, let us assume we are going to simulate some 50,000 samples with the mean of 2.65 kg with a standard deviation of 0.28 kg. Let us assume this is the range of data, the newborn Indian babies in India. This is just a assumption. It's just an assumption because we are going to simulate the whole process. Because just to simulate the process, I need to simulate population data, 50,000 samples. What is the best way to approximate this this estimation 2.65. In the reality, this value, the score is unknown to us, right? We are just going to estimate it. Assume I'm going to randomly select, let us assume some sample size of 500 as a fixed sample size of 500. Randomly, I'm going to select samples across the country, without any bias. Randomly, I collect 500 samples. And those 500 samples, okay, those 500 samples, I calculate the mean of those 500 samples. Okay, that mean I'm recording as X bar. And I'm going to repeat the whole process, one more round. Once again, I collect 500 samples. This time, 500 samples. Once again, I'm doing it randomly across the country. So I'm getting another 500 set of samples, and I'm getting a mean of that. Another round I'm doing it. Let us assume that I'm going to do this process for 50 rounds. Now you understand why it is an expensive. Practically, this data collection process, it involves the human resource, okay, the energy and time and the cost involved in the human resource deploying for the sample collections. Assume that if you are doing it for the 50 rounds, since here it is a computer simulation exercise you are going to do in software, but in the reality, we need to collect the samples. If it is a survey data, or it's going to be a market research data, whatever the applications you do it, for a political opinion poll survey, that kind of data, definitely we have to do the combining and surveying data. It involves the huge cost and time, right? So I'm doing this for 50 rounds. Now I got 50 such X bar values are there. Every time I got 500 samples, that X bar, now I got 50 X bar, the 50 mean value are there. Now I'm going to plot these 50 mean values. If I do the plotting, those 50 mean values are plotted like this. For example, the first round I may got around 2.5. The next round I may got 2.6. Another round I may got 2.55. In another round I may got one more time of 2.5, another time of 2.6, 2.45, 2.65, and so on. If I'm going to plot those data versus frequency or count, so I'm going to get a near normal distribution. This is going to be a very close normal distribution. It's going to be. What is this? This is the distribution of the samples every time you have collected. Every time we have done it for 50 rounds. So those 50 samples I'm going to plot. With the y-axis, the frequency of occurrence. So we call this as a sampling distribution. It is a sampling distribution. What the sampling distribution communicates? You are trying to estimate the population mean. But that estimation is found to be not as a point estimate, wherever you got some range of values. As a range of values, right? The standard deviation of the sampling distribution, yes, that directly tells what is the average error I make in predicting the population parameter mu, right? Sometimes I'm estimating value 2.7 kg, that might be above the population parameter. Of course, we are not sure about the score. Sometimes whatever the sample mean, it could be lesser than the actual population mean, might be 2.4 kg. Sometimes it could be equal. Some of the trial when you do it, that those 500 records could be exactly equal to 2.65 also, chances are there. But what is the average difference in your 50 rounds? That average difference is expressed as your standard deviation, right? As the average difference of so and so unit you get. So in your sampling distribution, whatever the standard deviation we obtain, that directly reflects the standard error of the mean. That directly reflects the standard error of the mean. Why you call it as a standard error of the mean? Because we are approximating, we are understanding when you are doing the sampling distribution, this is very close to normal distribution. So it means the standard normal distribution close to. That is why you can apply the same empirical rule here. Same empirical rule. What is the 95% confidence interval range of data of the range estimate whatever we have done? Whatever the average of these, all 50 trials, this mean value, that x bar plus or minus 1.96, this sigma, it is going to give you the 95% confidence interval range of your population parameter. Whereas the practical approach, when you come to the practical approach, which is very practically feasible approach, of course, it's a less expensive approach. We are trying to mimic the whole process. We are trying to mimic the whole theoretical process. But whatever we have approximated the population parameter with 50 trials or even 100 trials, the more the number of trials you do it, you get a better approximation of the distribution. It's close to, that's why we say it's a central limit theorem. So your distribution will come precisely close to a perfect normal distribution, which follows your empirical rule of central standard normal distribution. That is 68% of the data, your data falls within -1 sigma to +1 sigma, and 95% of the data falls in -1.96 to +1.96 sigma. But of course, in the very practical approach, what we do, I just do only one round of sampling. Only one round of sampling. Assume I have a budget of doing only one round of sampling. I just collect only one round of samples. Let me got 500 samples. That's all. I just plot these 500 samples. I just see the histogram of these 500 samples. Okay, I'm just seeing the histogram of this 500 samples. Please remember, this distribution is different from this distribution. We cannot directly compare this distribution with this distribution. This distribution is a distribution of every time I collected 500 samples, take the mean, another 500 records sampling, you take the mean. It is a mean of the sample distribution, right? Whatever you're doing, it is a mean distribution of the sampling distributions. Whereas here, I just collect only one round of samples, that is 500 samples I collect from the population randomly. Those 500 samples, if I plot, it might follow some distribution like this. And using these 500 samples, you calculate X bar, this X bar. Using this X bar, you have to estimate the population parameter, 95% confidence interval of the population parameter. So like the way what we have used, here the standard deviation S directly reflects the standard error of the mean, standard error of the population mean, what we are trying to estimate. However, since I just plotted the samples, these 500 samples, so this distribution is different from this distribution. So what we are trying to do here is, I'm just going to approximate this whole process Okay, the whole process equivalent to this more theoretical approach. You have done only one trial, whereas here you have done 50 trials. Whatever the results we obtained here in 50 trials, we are trying to approximate the results we got in just one trial. How do we approximate here is, I'm going to define the standard error here. What is the standard error here? The standard error is nothing but your sample standard deviation itself. This X bar, the deviation of the X bar, once you plot the histogram of these X bar standard deviation itself tells the standard error here. Your standard error is defined as straightforward your standard deviation itself. Whereas in this process, how I'm going to approximate the standard error here is, whatever the standard deviation of this distribution, which is obtained with one trial, that standard deviation upon square root of the total number of samples we have taken. So the standard error is defined as the standard deviation divided by root n, number of samples you have taken it. This is called as the standard error of the mean, in which this will be a close estimate of, approximate estimate of this S value. Hope you can able to relate it. This standard deviation is a close, we can relate the standard deviation with this formula, standard error of the mean, standard deviation divided by root n. You should have a clarity on understanding what is this standard deviation we are calculating from this 500 samples, whereas this is a standard deviation we calculated from this 50 samples. How these 50 samples are arrived? Based on the 50 trials. Each trial I picked 500 samples, take the average, those 50 samples are plotted. The standard deviation of those 50 samples directly represents the standard error of the population mean, whereas the standard deviation of these one trial 500 samples will not directly represent this standard error of the mean. So to approximate this theoretical process, what I do, divide by root n. This standard error of the mean and this standard deviation value will come near closer. But if you ask me which is the best one, of course this is a very close, better approximate. This is more practical approach. So how we are going to represent the 95% confidence interval range estimate of the population mean using this approach is this X bar, okay, plus or minus 1.96, this standard error, whatever you have calculated, you have to substitute this. So this is the logic. I'm going to demonstrate this in Python. Let us see the simulation in Python. So to simulate the samples, I make use of NumPy package rand-n function. As you are aware that rand-n function will generate samples normally distributed, but in the reality, your population need not be following any strictly following normal distribution. It can follow any distributions. So the beauty of the inferential statistics is, irrespective of your population distribution, we are going to estimate the population parameter by approximating your samples close to the near normal distribution, and then we are going to estimate the population parameter. So however, here I'm simulating 50,000 samples, just simulating our example. Let us assume that the average weight of the newborn baby for full term, the population parameter I have assumed as 2.65 kg as a population mean with a standard deviation of, let us reduce the standard deviation to 0.275. Okay. So hope you have used this rand-n function. Those who have used this rand-n function, you aware that the rand-n function will generate samples between 0 to 1. Sorry, -3 to +3. Of course, we can have samples beyond the -3, beyond +3 also, but those frequencies will be very less. because your 99.75% of the samples are distributed within -3 to +3 sigma, with a mean of 0, 0 mean, and with the standard deviation of 1. That is a standard normal distributed samples. X bar is 0 and standard deviation is 1. This is a characteristic of standard normal distribution. Standard normal distribution. This point we have discussed in our previous video also. In normal distribution, right? So random.random function in Python, which is going to give us the range of values from -3 to +3. This is standard normal values. We are going to simulate the samples in the real world unit. We know the relationship scaled data, standardized data as x minus x bar divided by standard deviation of x. This is a relationship, right? This is your value after standardization. This is the value in your real world unit. Suppose you wanted to simulate the samples in the real world unit, by default random function will generate the samples in standard normal values. But if you want to simulate the samples in the real world unit, whether you wanted to simulate age in years or income in Indian rupees or US dollars, euro, whatever the quantitative variable you wanted to simulate, okay, we can simulate using the same random function. Okay, just you have to represent your real world values, what standard deviation at what mean value you wanted to generate. So just you think that you just take a cross multiplication of this, how you can represent your x, your real value. This is the range of values we generated using random function. That has to be multiplied by standard deviation. You bring this minus x bar to the left hand side, it becomes plus x bar, right? So I can have a relationship like this. So standard normal distributed samples multiplied by the required standard deviation plus x bar will simulate the samples as per our real world units. So we are simulating 50,000 samples as per the real unit. So I store the result in p variable as the population in standard normal unitless, of course. Now I multiply with the standard deviation. 0.275 is the standard deviation we just assumed, and 2.65 kg is the mean value, kilograms. So after simulating this 50,000 samples in the real world unit, you can see we have simulated very close to the real world unit. The mean of this population, I'm storing the result in POP variable. 2.65 is the mean, and what standard deviation we simulated? Close to 0.275, 0.2748. So 275 is approximately, this is 275. In fact, as we increase the sample size, we can bring it very close to the approximation, to the value what we are trying to simulate. We can bring the value very closer by increasing the sample size. You can see after simulating the samples, the minimum and maximum range of the population what we have created, 50,000 samples, okay, with the mean value of 2.65 kg. You check the min value of the population is 1.5, possibility is there, right? A lot of places very underweight, malnutrition babies are there, because since the samples is taken randomly across the country, so some of the places, very rural areas where the malnutrition baby also, though it is a full term, we may have a weak 1.5 kg up to the upper limit 3.79 with a standard deviation of 0.274 grams, right? So we have simulated the population data, and if you wanted to visualize the population data, since we have used random n function, normally distributed samples, so your entire 50,000 samples is a perfect normal. Even you can simulate this with some other distribution also. Still we can do the estimation of the population parameter. See what I'm going to do. This is a very practical approach. The very practical approach is what I do just one round of sampling. So how do I do that? That one round of sampling is 500 samples I need to collect from this 50,000 samples, right? So I'm going to use a function random.choice. This random choice function randomly pick one sample from this 50,000 samples. If I run this for one time, it will pick one record. 500 times I'm going to run this inside a for loop. When I run this inside the for loop 500 times, I'm going to append those values in the variable called sam. So now it is going to be like a list of numbers. My SAMP is going to have these 500 records. So after running this, you can see your SAMP variable will have 500 records, which is being randomly picked. You can see 2.46, 3.2, 2.98, 2.96. This is the samples, 500 records. And I'm taking the statistics of this 500 record mean. That 500 record mean is found to be, let us calculate the mean and standard deviation of this, 2.6233 kg with a standard deviation of 0.268. So this is the standard deviation of the samples, right? 0.268. But this standard deviation is not directly representing the standard error of the mean of the population parameter. So what is the approximation we do? Whatever the standard deviation we obtain, that has to be divided by the root of the total number of samples taken. So 0.268 divided by root 500, that is going to give us the standard error as 0.01198. Okay, this is a standard error. So once we know the standard error, we can give the range estimate of the population parameter. What is the sample mean? 2.6239. 2.6239 plus or minus. Let me take the lower value, 1.96. So anyhow, we have calculated this separately in SC variable, right? Let me put SC, standard error, minus 1.6. So 2.6239 minus 1.96 times SC. This will give me the lower boundary of 95% range and the upper boundary plus. So what you can say, this is a very practical approach. From the sample, how we are inferring the population parameter mu. Okay, the 95% confidence interval range, confidence range of population parameter. Here it is a mu. In the reality, we don't have any idea of this mu, but we can give the range estimate as, what is the lower boundary? 2.6002, okay, 2.647. Let us once again, let me verify the sample mean and standard deviation. Sample mean, .271. 0.012, because I have edited the required standard deviation here. After editing the value, I didn't rerun this loop, so I reran that loop. Now this is the actual mean and standard deviation of this 500 samples. So 0.2715 divided by root of 500. This is my standard error. Okay, now let me update this. Also, mean also changed, 2.639. Since we have not set the random state, every time you run that loop, you get another set of new 500 samples. Okay, doesn't matter which 500 samples you take. Ultimately, your 95% confidence interval range should contain your population parameter mu. Point 639. You can see actually this is the correct range, 0.615, 2.615 to 2.662. Since we only simulated the records, we know it very well. What is the mean value we have simulated? 2.65 kg. You can see that 2.65 kg is very well contained in the interval 95% confidence interval range. So the smaller the standard error, what it implies that you have a very closer estimate. You are getting a very close estimate of your population parameter. Let us try to do this. Even if you wanted to see the histogram of the 500 samples, what you have collected, this is a histogram, corresponding histogram. Yeah, this is also very almost near close to perfect normal. And I'm going to demonstrate this very theoretical approach, very theoretical, and it's a very expensive approach. I'm going to do 50 round of that 500 samples, because every time I run this 500 samples, we got no different mean. Just now we have noticed the same loop. If I run this for one more time, that time I get the mean of, because those 500 samples mean I'm displaying here. Every time I run the loop, I get the mean. My mean values are keep changing, right? Fluctuating. Assume that 50 times I run the loop, that is equivalent to I'm keeping a variable called trial. Okay, this trial, I'm going to collect those 50 trials, every trial. Okay, you can see how this for loop, this nested for loop works. So for every trial, because the trial is mapped in np.range of 50, I'm going to have this 50 trials. So for every trials, I'm going to pick 500 samples. I'm taking 500 samples, and those 500 samples are appended in the variable called SAM. And every time I'm taking the mean of that SAM. The mean is appended in the trial. Okay. After running the trial, you can see the length of the trial. We got 50 values. If you want to see those 50 values, individual values, you can see these are all the 50 mean values. So every time we took 500 samples, that 500 sample mean. Another time 500 samples, those 500 samples mean. So this is practically little expensive approach. Now, the beauty here is the standard deviation of these 50 samples directly represents the standard error of the mean, right? That's what we have discussed. So the standard deviation of these trials, 0.0117 as a standard error. What is the standard error here? 0.0121. when I do only one round. When I do one round, how our standard error of the mean is approximated with one round. Whatever the standard deviation we got, that is 0.2715 of these 500 samples divided by root of 500 gives the standard error of the population mean is 0.01214. Whereas in the second approach, which is more theoretical and very little better accurate approach, but of course it's a little expensive approach. The standard error comparatively is less. You can notice the standard error is comparatively less. There it is 0.012. Here we got 0.011. How to intuitively understand the standard error? Let me explain little intuitively the idea. What we are doing here, what we do, every time I pick 500 records, take the mean, another 500 records, take the mean. Okay, those 50 records, like we are doing it for 50 trials, and I plot these 50 samples, and from that distribution, whatever the standard deviation of those 50 samples directly represents the standard error of the mean, right? How to intuitively understand this? Assume when I can get the standard deviation will go zero, when the standard deviation of the 50 samples can go zero. In fact, my that is my standard error of the mean can go zero only when I do the point estimate, right? Only when we do point estimate. Assume instead of 500, assume if I access the entire 50,000 my population, assume the population is fixed. Practically we don't do that, but just to intuitively understand the meaning of this, how the standard deviation of these 50 sample directly represents the standard error of the mean. To appreciate this concept, from the population pick entire 50,000 samples. What do we get? Exactly 2.65, right? Another time you pick entire 50,000 samples. Once again you'll get 2.65. In all the 50 trials, I'll precisely get 2.65, 2.65. If you see the distribution of that, second time, third time, this value is 2.65. Fourth time, fifth time, and so on. 50 times, you get a vertical line. This is how your distribution looks. One single vertical line. What is this one single vertical line at 2.65? It is a point estimate of your population. Now, what is the standard deviation of this? There's no deviation. Standard deviation is zero. So my standard error of the mean, because after all, you have done the point estimate. There is no scope of the mean error. So this is a very point estimate, but practically we don't do this, right? It doesn't, the entire population, if you have the facility to access, then why we do the inferential statistics? So we are doing the inferential statistics because your population is it's a varying population. We cannot exact the entire population is not accessible. So we go for the inferential statistics. In inferential statistics, we pick random samples from this. From the 500 samples, we are going to say that whether this 500 sample mean is a representation of the population or not. How we give this? We are giving this representation in the form of 95% confidence interval range. But however, we need to prove this as a hypothesis. Whether my sample mean is a representation of the population, it is a one sample mean test we need to perform, one sample t-test. So I'll be discussing this hypothesis testing in the next subsequent video. So that is the next topic for the discussion. But here we should be able to represent the population parameter in terms of either 95% confidence interval or 99% confident interval or 90% confidence interval. What will happen as you keep on reducing the range? But every time you may not get the 2.65 when you go with 500 samples. So we got some range, right? We got normally distributed samples. Suppose if you are representing the range with 90%, so 1.64, 1.64 sigma minus 1.64, 90%. As I narrow down my range, my confidence level in estimating the population mean will come down, right? My confidence will go down. So I represent the answer with a broader bandwidth. If I represent the answer with a more and more broader bandwidth, I have more confidence in telling that my population mean will fall in the bandwidth. You have a larger bandwidth, you have a high chances of your population parameter to fall in the bandwidth. As you keep reducing the bandwidth, your confidence level also go down, right? So that is how you can understand intuitively, you can understand your confidence intervals. Here, what we are concluding in the Python simulation here, coming back to the Python simulation. In 50 trials, the 50 trial mean value 2.648. Now, directly the standard deviation represents your standard error of the mean. So let us see what is the lower and upper bound of these value. 2.625 lower bound and upper bound is 2.6717. So 2.648 minus 1.96 time of this standard deviation. This is upper bound. So the 95% confidence interval range is 2.625 kg to 2.67 kg. So this is with the more theoretical but expensive approach. The more practical approach, you get only one round of samples. When you get one round of samples, this value, you cannot directly substitute the standard deviation of those 500 samples. That standard deviation should be divided by root 500. Then only you can substitute that as the standard error of the mean. So that's the difference. Hope you understood how do we estimate the range estimate of the population parameter. Okay, so some of you might ask me, this is a very mostly asked question whenever I teach this. How do we do this, the range estimate for the qualitative variable? Okay, this is fine, it's a quantitative variable. In fact, it is a weight, right? A weight in kg. Suppose when I have my estimation parameter is qualitative, say for example, you take some samples, okay? Suppose let us say some exit poll survey data you collect, okay? Which candidate you have voted, okay? Suppose what is a proportion? What proportion of the entire state has voted for this candidate, so and so candidate? You wanted to estimate, okay? The proportion of, suppose you collect some samples, you ask whether you have voted for this, but actually the problem statement is, let us say the candidate X, okay, after the poll, you are asked the people coming from the polling booth, you are asked the survey data, whether you have voted for this candidate X or not. So some of the people say yes, some people say no, okay. So you get a qualitative variable. You have collected some around, okay, let me take some example, like 142 cases are yes, and 108 cases said no. So out of 150, randomly picked 150 candidates from the polling booth, what you have interviewed around 142, sorry, 250, right? So 250 candidates we have interviewed. So we have asked, have you casted vote for this candidate after polling? So for exit poll prediction. So before the official result is being published. So the various organizations, they give the exit poll survey, right? Now I wanted to see that what is the characteristic of the entire, is it possible to infer the entire population? What percentage of the people has casted vote for this candidate? Is it possible to infer the Population parameter, here this is a proportion. What proportion of the candidate has voted for this candidate? Here in the sample, out of 250, 142 people has casted vote for this. So what is the proportion? What is the proportion of the sample for the candidate? Casted vote for the candidate X is 142 out of 250, right? It is 56.8, approximately 56.8%. Now the question is, how do we estimate the population range? 95% confidence interval of your population range. So let us call this is like a Bernoulli distribution, right? This is you can call the S cases as 1. This is you can call it as a P. This is 1 minus P. Okay, like how do you substitute the value for your mean and variance calculation for the quantitative variable? Here also we can estimate the mean and variance. This is proportion. In qualitative variable, this proportion is equivalent to your mean calculation in quantitative variable. So in the same sense, if you wanted to do work out that calculations, I would do it like this. So strictly like that mean calculation. How do you calculate the mean from the histogram of a continuous variable? Suppose we have a histogram of a continuous variable. So every continuous variable with respect to frequency we have, right? Suppose you imagine for a quantitative variable. Suppose I have age. There are 3 counts. This is 18. There are 4 records. And 20, we have maybe 5 records. 22, I have 3 records. Suppose if I ask you, this is a quantitative variable, let us say age. What is the average age from the histogram? So 15 times 3 plus 18 times 4, 20 times 5, 22 times 3 whole divided by the total count, right? Same way we can work out this 56.8, the same way you can work out. Whichever the proportion you are supposed to calculate, keep it as 1, or the another category you can keep it 0. How do you calculate the proportion here? 1 times 142, 1 times 142 plus 0 times 108 whole divided by the total count 250. So obviously this will go 0. So 140 divided by 142 divided by 250, same as 56.8. In the same way, you can calculate the variance. So how do we calculate the variance? Each and every value x minus x bar the whole square sum divided by. So this is your variance formula, right? Summation of xi minus x bar the whole square summation divided by n minus 1. I varies from 1 to n. So same way we have 142 ones are there, right? So 1 minus 0.56 plus another 1 minus 0.56 plus another 1 minus 0.56, like 142 times we need to do this. So that is equivalent to 142 times of 1 minus 0.568 whole square plus 108 times of 0 minus 0.568 the whole square whole divided by degrees of freedom total record 250 minus 1. We'll get this is the variance. If you simplify this, we'll get 0.246 and take the square root for this, you'll get a standard deviation of 0.50. This is just one round of sampling. Remember, we need to do the approximation. What is the standard error of the proportion here? The standard error of the proportion should be done. This standard deviation, okay, the standard error of the proportion here is 0.50 divided by root 250 samples. You will get around 0.031. So once we got the standard error of the proportion, we can represent the 95% confidence interval range. So 0.568, okay. So 0.568 plus or minus 1.96 times this SEP, that is 0.031. If you simplify this, you'll get the lower bound and upper bound. I have roughly calculated that is found to be 50.72 percentage to 62.8 percentage. 62.8 percentage. So the population proportion will be lying in this 95% confidence interval range. So from the sample data of 250 records, so we can infer the strategy of the entire state, how they have casted the vote favorable to the candidate X. So here we did the whole calculations as a proportion range. So even it is whether it's a quantitative variable or a qualitative variable, we can estimate the population parameter with a range estimate. So this is the first level of confirmation whether our population parameter falls in this range, but still I need to prove this with a hypothesis testing. How do we perform the whole process with a hypothesis testing? Now that boils down to one sample t-test. Okay. In the next session, I'm going to talk about this one sample t-test. How do we conduct this one sample t-test? What is the scope of this one sample t-test and its different flavors? So we can do one sample mean test as well as one sample proportion test. And what are the functions in Python we'll be discussed in the next video. Thanks for watching. So have a very good day. Thank you.